Hello, and welcome to Science Journeys, Caltech's first online science education series. I'm Michael Alexander, the Director of Caltech's Public Programming, and I'm very happy to have you all with us today. Caltech is one of the nation's premier science education and research institutions. In fact, Caltech created the Jet Propulsion Lab, JPL, which has managed most of the United States' unmanned space flights. As we speak, there is an unmanned space mission on its way to Mars that includes a helicopter that will be the very first to ever fly on another planet. Our office is also responsible for bringing to the campus the Performing Arts series that takes place here in Beckman Auditorium. We would encourage you all to look to our website, where you can find out about all of the lectures and performing arts series that are going on here by going to events.caltech.edu. Today, I am proud to introduce Salvador Gomez, one of Caltech's outstanding scientist scholars. He is a member of the Club Latino, which has conducted many demonstrations. I'm sure many of you know that STEM stands for science, technology, engineering, and math. And we've done that play on words as he is going into schools throughout the Pasadena area to give lectures to young students. Mr. Gomez is a Caltech grad student who also has been doing some very exciting research work on our campus. Today, he is reaching out to new and engaged audiences through this internet project. We are presenting this from Beckman Auditorium, which is right here on the campus, and we look forward to the day when all of you can come and see these programs in person. He is studying aerodynamics and is on his way to his own PhD. Of considerable interest, in addition to his work on campus, is his personal story. He is going to share information about his middle and high school years that I know will be very interesting to all of you, and it reminds me what an exceptional scientist he is. I know that you're going to hear fascinating information about the science he studies as well. So now, with great pleasure, I welcome to the stage Salvador Gomez.
Thank you for the introduction, Michael. I'm Salvador Gomez, a second-year graduate student at Caltech. I'm studying aeronautics, and I'll be talking to you guys about fluid dynamics, specifically how we go from disturbances and how we move on to turbulence. So I'll start off with a little bit about myself. I'm Salvador Gomez, a first-generation college graduate student. That means I'm the first in my family to have gone to a university. I grew up in Hayward, California. Here's a picture of my family on the left. And I went to school in UC Berkeley, a few cities away from where I grew up. After getting my degree, I came to Caltech to get a PhD. And a lot of people, they focus on where they started and usually jump to where they're at now. But I think it's important to focus a little bit on the details. So growing up, my life was pretty uncertain. When I was in middle school, around 8th grade, my life kind of changed and was going through a lot of turmoil because my mom passed away, and because of the recession going on, my dad was in and out of work and was having trouble finding a steady job. My dad was able to make ends meet using the truck that you see in that picture by recycling scrap metal. So every day I would come home from school in high school, and I would help out my dad with his work, and I would also, cook for the family, clean up the house, try to make it a little nice for me and my brother and my dad. The only thing I found to really distract me from all the stuff going on at home was school. So I was really good at school, but college was not on my list. It wasn't something I had on my mind. Part of the reason was because, like I mentioned, I was the first in my family to go to college, so nobody around me had gone to college, none of my neighbors had gone to college, and it was just me. So I had to really figure out what I wanted to do with my life. So thankfully, I was around friends that had goals. They all had goals to go to college, and they had an idea of where they wanted their life to end up. Around junior year, so 11th grade, I started thinking about what I really wanted to do, and things started really started to click. So things started to click because I looked around what was going on in my life. I knew that I didn't want to work such a backbreaking job like my dad, lifting these scrap metals, lifting these broken appliances and breaking them apart to get the recycled material. So I figured I wanted to do something that could make that type of work a little bit easier for my dad and make things a little bit more sustainable. So still working on recycling, but on the design aspect. So how could I make these appliances a little bit easier to recycle and have less of a carbon footprint? So that took me to basically 3 steps. I wanted to think about the life I wanted to live. So I wanted to live a more certain life. I didn't want to struggle finding a job. I didn't want to work a really hard, back-breaking job. I thought about what I was good at, and for me that was math and science. And it felt like engineering could take those skills that I had and that passion to create sustainable products, and it seemed like a good way to mend the two. And finally, I had to think about what could actually take me down that path. So what could make me an engineer? It turned out that was mechanical engineering, and to go down that path, I had to go to college. So that eventually led me to applying to UC Berkeley, and that's where I ended up studying mechanical engineering, and where I started feeling a different set of struggles. So one of these struggles was imposter syndrome. Imposter syndrome is a belief that you do not belong or that you got there through luck. So being one of the few Hispanic students in my classes, being one of the few first-generation college students, it really felt that I didn't really belong in this place because all my peers had parents that were engineers, parents that were professors, parents that had gone to college, and they seemed way more equipped than I was. But I knew that I belonged there, and I had to really learn how I can succeed in this new environment. And for me, being able to succeed in college was learning how to study. So for the first time I was able to learn how to study. I was able to make friends that knew how to study and were able to show me the ropes, if you will. And I started enjoying my studies again. I was able to really enjoy school because I was doing really well. So because of that, I got the opportunity to teach, and I got the opportunity to teach more students how to learn and how to study. And here you can see a picture of me studying with some of my classmates and even teaching a class to some freshmen. So those opportunities led me to want to go into academia. So I wanted to become a professor so that I could teach for a living. So when you become a professor, you have to decide what you want to research. So usually when you become a professor, you end up becoming an expert in a certain field. And for me, I ended up being really interested in fluid dynamics. So for those of you that don't know what fluid dynamics is, it's basically the study of, fluids. So a fluid is basically any substance that can move freely by outside forces, such as liquids, gases, and plasmas. The dynamic side is basically understanding how things move as a result of these external forces. So it's basically applying physics to gases, liquids, and plasmas. And as a fun way to think about it, you can think about this based off this cartoon, Avatar: The Last Airbender. So the main character, the guy in the orange, is able to master all 4 elements: water, air, fire, and earth. And what I argue is that if you study fluid dynamics, you can become the Avatar. So if you study fluids, you're able to understand how the oceans move, so how water moves. You're able to understand how storms and clouds form and move around. So you're able to understand air. You're able to understand combustion. So here we have some rocket science, and you're able to understand how these things can combust and burn up. So you're able to understand fire. And you can even understand how hot lavas in the earth are able to move the plates. So you're able to understand Earth. So I argue that if you want to become the Avatar, study fluid dynamics. But there's more of a reason to understand this. So apart from knowing how things move, you're able to really make predictions and you're able to make design. So the motions that explain how coffee behave are also able to explain how we see storms and ocean waves. So here you can see two different aspects. You can see planetary things like in Jupiter and things as small as in a cup of coffee. There's also billions of dollars that you can save if you understand turbulence. So if you're able to understand the drag that certain bodies move against oceans or air. So if you've all heard about air resistance or drag, that's one thing that we want to try to work on. So there's several ways to study fluid dynamics. The first way is going through an analytical route, and this is what people have been doing for maybe the past couple hundred years. And what it involves is studying the equations of motion. So it involves studying the equations that govern fluid dynamics. So these equations, the Navier-Stokes equations, are so hard to solve that there's literally $1 million prize for anybody that can just prove that a solution exists to these equations. So if you're able to just prove that these solutions exist, you can get yourself $1 million. It seems pretty trivial, but there's actually a lot of math going on in these equations. So there's several maths that you need to understand to understand this equation. You need to understand algebra. So I'll show you an example of how we need algebra. You need to understand linear algebra, which you'll maybe see in high school, but you'll definitely see in college. You need to understand calculus, which you'll see at the end of high school and maybe at the beginning of college. You also need to understand real and complex analysis, which you'll see at the end in your college degrees if you study math. And finally, there's also math that we haven't even invented yet. So there's avenues that we haven't explored and can still be discovered. So because the fluid dynamics equations are so hard to solve, but we still have to deal with them, there's several ways that we can get away without solving the equations. The first way would be by simulating the problem with computers. So here you can see an airplane wing, so it's just a cross-section of the airplane wing, and we can see that it's being simulated by flow going over the wing. When I talk about simulations, what I want to talk about is approximating the flow with a computer. So one way I can think about this is if we think about a video game. So here on the left, we see a pretty rendered image that you'll probably see like on a Nintendo Switch. And on the right, you see what I grew up with and maybe your parents grew up with. And that's what we had to play video games with. So you can see how boxy and square the one on the right is, and you can see how smooth the one on the left is. So we can think of the one on the right being a simulation because it's supposed to represent the one on the left. The way that it's done is that the simulation takes a field, so for example, the air around the airplane wing, and it breaks it up into little squares, so little tiny cells. And what it does is that it basically does algebra. So it takes one cell, and based off the cells around it, it's able to solve for what's going on. Because you're doing a simulation on these tiny, tiny little cells, you're able to treat the problem as an algebra problem. And all you have to do is basically solve these algebra problems for everything on the field. Back in the day, so if you watched Hidden Figures, this is something that people actually had to do by hand, and there was actual offices of people just computing these things by hand. But nowadays, the computers can do this for you. They're so efficient at it that they're able to compute all these algebra problems in a matter of minutes or seconds and simulate the flow around an airplane wing. We can also see like examples of these simulations, and here's an example for a simulation that we can see online if we click on the following link. So in this simulation, we basically have fluid inside a square container, and if we move the cursor around, we're able to simulate what it'd be like to mix the fluid. So you can probably try this at home by clicking the link, or you can even have a cup of milk and you can put some food dye and just trace it around, and you would get similar pictures. So the last way is doing things by experiments. So that's where we take measurements in a controlled laboratory setting and simulate something in the real world. So again, we have the airplane wing, and we have air coming to the right of it. So it's meeting some air coming at it. And what you're seeing is path lines. So each of these little lines that you see are lines that a particle would follow as it flows around the airfoil. So just as this little orange thing finds and swirls all around, this is what experimentalists look at. They try to understand, they put a bunch of particles in a flow field and let the flow move around it and basically trace out where these particles move in the fluid. Usually you need photographs so that you can take a picture of this and see all these particles in motion. You can also think about it like if you have a long exposure and you take a picture of a moving light, you can trace out the light. That's basically what experimentalists do when they do some of these visualizations. You can also see it if you have a fluid dye, like food dye, or if you put smoke and you can see like smoke coming out of a chimney. So as good as these computations or experiments are, they still have some hard parts. They still have some things that doesn't make them perfect. So what makes it hard in a computational sense is that computers are not strong enough to simulate everything in the flow. So just how the newest video game systems probably can't simulate every single thing in the real world, that's the trouble that we're having with our simulations. Experimentally, the issue that we have is that sometimes there's really tiny features or really big features that are really hard to measure. So one way that I can think about this is think about a shark. So a shark is a macro scale, so it's like maybe the size, maybe like 10 feet long. And then it also has shark skin that makes it move very efficiently. And these shark skin are on the micro scale. So the shark skin have features that are as thick as a human hair. So if you really want to understand how a shark moves, you need to understand how its body moves, so how its body behaves. But you also have to be able to measure these tiny little scales. So you have to measure the tiny little skin on the shark so that you're able to understand what makes the shark so efficient at swimming. And what it really comes down to is that it gets expensive. You can probably do this if you just throw enough money at it, get a bigger and bigger computer, or get more and more precise measurements. But sometimes it isn't really affordable or it isn't really practical to do this. We have to really understand what the difference between a scientist and an engineer is. So a scientist will tell us what's going on physically, and they'll let us understand what's going on in the equations, and they're really interested in understanding more about the natural world. An engineer, on the other hand, tries to solve these problems with the equations. They try to simplify it as much as they can while still holding the relevant physics to try to make some progress and understand what's really going on so that you can make designs or make predictions. So what engineers do is they try to model the fluid. And when you want to understand these equations, the Navier-Stokes equations that govern the fluid, we need to understand the different fluid properties. So fluids have something called density, which is their mass divided by their volume. That's what tells us which fluid is heavier and which fluid is lighter. So one way that you can think about this is by comparing things that you might be familiar to. So one of these things is a baseball and a tennis ball. So although the baseball and tennis ball have about the same volume, they're about the same size, baseball is heavier than the tennis ball. The reason for this is because the baseball is denser, so it's heavier, and the tennis ball is less dense, so it's lighter. And you can think about this by trying to understand what's inside the baseball. So if you look inside the baseball, you'd see a bunch of material inside, but if you look inside the tennis ball, you would see basically just the casing and a bunch of air inside. Because of this, we'd say that the baseball has more stuff, so it's more dense, whereas the tennis ball has less stuff and it's less dense. You can also think about this if you've ever tried to do this experiment where you try to stack different fluids. So here we have a stack of fluids in a cup. We have vegetable oil, water, dish soap, and corn syrup. And we can see that the less dense fluids float on top of the more dense ones. So the denser ones start to sink, and the lighter ones rise up. We can also understand How this works, if we think about hot air, so in a hot air balloon, you heat the air, and because it gets hotter, it rises. So hot air becomes less dense, and it's able to float when it's around cold air. The next of these properties is viscosity. And basically, viscosity is the resistance to motion. And what we think about it sometimes is how thick the fluid is, and we denote it by mu. So here you can see a video of 4 different fluids being poured down. We can see that the corn syrup and the honey flow down pretty slowly, whereas the dish soap and the maple syrup flow down pretty fast. Because of this, we say that the honey and the corn syrup are more viscous than the other two. Another way you can think about viscosity is think about the difference between walking in our everyday environment where we're surrounded by air and walking in a pool where you're surrounded by water. So if I walk around here, I have no issue and I'm able to walk around pretty freely. But if I walk around in a pool, I have to really struggle to move my body because I have to move against the resistance of the water. You can also think about this if you're trying to mix a cup of water or a cup of honey. The next thing that we look at with fluids is we are really interested in their velocity. So their velocity is basically how each part of the fluid moves. And there's different ways that we can visualize the velocity, but ultimately this is what we try to capture with these Navier-Stokes equations. Basically, the Navier-Stokes equations are force equals mass times acceleration. So they're basically Newton's laws applied to a fluid. So basically what F equals ma tells you is how much force I need to apply to move an object. So here I have 2 different boxes. One is 10 pounds and one is 1,000 pounds. Because they're on Earth, they have weight because of gravity, so they have a force due to gravity. And if I want to move the boxes, I need to apply different forces to it. So if I want to move the 10-pound box, I need to apply less of a force than if I wanted to move the 1,000-pound box. So if you really want to move these boxes, you need to overcome their weight. There's several forces that act on a fluid. The first of this is pressure. So pressure is the force from the fluid atoms as they move around. So it feels like something's pushing against the walls. So here in this balloon, we see all the little fluid particles trying to move, they're bouncing around, and they're trying to expand and push against the balloon. So that's why when you blow air into a balloon, it expands because the air molecules are just bouncing around, pushing against those walls. The next one we feel is friction, and friction is usually due to drag, and it's what you feel when you move against the fluid. This friction is caused because of the viscosity. So here you can see a plate being dragged across some water. And you can see by the smoke visualization that it causes the smoke around it to move around. And you can kind of visualize how the turbulence is affecting the drag. So if we put all of that together, we get the Navier-Stokes equations. And we can dissect each part of this equation. The first one on top basically tells us what comes in must go out. The second one is a little bit more complicated, and then that's the force equals mass times acceleration. So the stuff on the left-hand side is the mass and acceleration, and that's where the density will come in. On the right-hand side, we have all the forces. So we have pressure differences, viscosity, and we have effects of gravity and density. So although this may seem complicated, we can try to understand this by making simplifications. One of my colleagues once said that life is like the Navier-Stokes equations. It may seem complicated at first, but once you identify the important terms, it will become clear how do you make progress. So although these equations seem really difficult, there are ways we can try and simplify the equations to actually solve some problems. So sometimes we know that there's going to be a tiny disturbance in the flow. So here we have some fluid moving through a pipe, and it's moving from left to right. But we see that there's tiny little disturbances that are not really going from left to right, but they're small. So the overall fluid is going from left to right, but these tiny disturbances are just causing some difference in the flow. So we try to model these equations, and we write these equations for the disturbance. And you can think of these equations as something familiar. So if you've done a little bit of algebra, you've probably studied y equals mx plus b. And if you've studied a little bit more of algebra, then you've probably studied this equation for a parabola. And you notice here that in the blue, there's something raised to the second power, so something quadratic. And this quadratic thing acts pretty interestingly if you have something really small. So if you have something like 0.01 and you square it, it becomes even smaller. So we can use this idea that these quadratic things, these highlighted blue things, if you have something small, they become even smaller. We can use this idea to do something called linearization. So here we're plotting the parabola from x equals 0 to 10, and we're also plotting the line from x equals 0 to 10. If you're going from 0 to 10, you can see that there's a big difference between the two. But if you look at a smaller domain, so if we zoom into maybe some region where x is really small, we can see that they pretty much sit right on top of one another. So if you're looking at x really, really tiny, you don't have to consider the highlighted blue term. You don't have to consider the quadratic term. You can get away with only considering the y equals mx plus b term. And that's what we do when we study linearized equations. A really simple example, so this is where we sit two different fluids on top of one another. So these two fluids would have different densities. So you can think of two different examples. One example would be a glass with oil and water on top. And you know that nothing's going to happen because the oil and water don't mix, and because the oil is lighter than the water. But if you have the other case where you have something with more density on top of something with less density, so you have a heavier liquid on top of a lighter liquid, you know that they're going to start mixing and things are going to get pretty messy. So depending on the fluids that we choose, we get different behavior. So one is stable, where you can have a nice clean line between the two, and the other is unstable, where you have mixing occurring. So when we try to understand this, we call this stability. So we try to look at these linearized equations, and we try to model a disturbance between the fluid as a wave. So it has some characteristic length and some characteristic speed. And what we're interested in seeing is how this wave will grow as a function of time. And it turns out that it grows by a growth factor. This growth factor will tell us if it's stable or unstable. So if it's stable, the disturbance won't grow. But if it's unstable, the disturbance will grow. So here we plot out the disturbance. You can see here that in this case, there's no growth and it's stable. You can have another case where the disturbance will actually shrink. So you can start off from the original wave and it'll become smaller and smaller and smaller. So this is also stable. Or you can have the other case where it's unstable, where the disturbance just keeps growing and growing and growing. And we can look at this physically. So in the case where the disturbance doesn't grow, you can think about this as a nice calm ocean waves. So when the ocean is really calm, like there's no storm or anything like that, you'll have that the waves just oscillate pretty nicely and they don't grow, they don't change, they just stay nice and uniform. And we can also think of another case where it's also stable, such as when you have the oil and the water. So here, any disturbance between the two surfaces of the water, of the oil and the water, will just decay and shrink. But you can also have something unstable. So this is when you have the milk and the coffee. So if you have milk, it's more dense than the coffee on the bottom, and you actually get it to start sinking, and you get mixing. So if you look at the two, here you can see a close-up of what's going on between the water and the coffee, and between the coffee and the milk, and you can see that it starts shrinking, and you have some length scales, but you still have some stuff sinking down, and that's because the disturbance has grown. But you can also take advantage of this instability to make some art. A Mexican muralist developed a painting technique that uses these ideas to paint cool textures. So he's able to use the linear instability to develop really nice painting textures. So the way that he's able to make these cool paintings is by placing a heavier fluid on top of a lighter fluid. So you get a heavier paint and you put it on top of a light paint, and then you just let it sit, and you get these patterns that begin emerging. So here you can see how you have the white paint on top of the black paint, and then these patterns just start to emerge. You can actually do this at home if you have two different paints. All you have to do is figure out which one's more dense. Usually the dark one is less dense. So you pour a thin layer of paint, and then you pour another thin layer on top of that one. And after a minute or two, the features will start to appear before it dries. So you can actually try this at home, and you can hopefully recreate some of these cool paintings. So now we'll get to a little bit about what I do in my research. So in my research, we try to understand turbulence. So that's where you have a disturbance that basically grew out of control, and now we have a lot of mixing going on. So when people usually think about turbulence, they think about airplanes when they started getting dizzy. So you've probably encountered this if you've been unfortunate enough to be in an airplane that starts shaking. But the turbulence that we're interested in is the turbulence that is around an airplane at all times. So this turbulence is usually seen on the wings of the airplane or on the surface, and it's caused when the airplane tries to fly against the air. So as it tries to displace the air around it, it starts to drag on this air, and because it's going so fast, it causes it to mix a lot. And it ends up causing a lot of drag. And it ends up being something that costs airline companies, shipping companies, billions of dollars, because this drag just ends up costing so much in fuel. And what turbulence is basically when flow is characterized by strong mixing and vortices of different sizes, and the flow is very irregular. Vortices are basically swirling fluid, and a lot of people used to think about this as randomness, but there's order to the madness. What some people think about it is by identifying things of different sizes. So here in this drawing, you can think about different vortices, so different swirling fluids of different sizes. So you have really small vortices near the bottom, and you have larger vortices at the top. This makes sense when you look at it at some experimental snapshots, and you can see that near the bottom of that snapshot, there's a lot of mixing and a lot of really tiny features, but outside of the snapshot, there's really big vortices. So if you recall the shark, we can think about the smaller vortices being affected by the shark skin and the bigger vortices being affected by the bigger parts of the shark. So if we really want to understand what's going on at the small scale, we should probably target the smaller vortices. So this is a really hard problem to solve. One way that we can start to make some progress on this is by borrowing some ideas from image compression. So when you take a picture, you save a bunch of numbers representing each part of the picture, known as a pixel, and you save that as a file. So if you have a megapixel, that ends up being 1 million numbers saved. And it ends up being that if you want to take a bigger picture, you have to get a bigger file size. So if you want to decrease the size of that file, you can try to compress the image. And what that entails is breaking up the picture into a bunch of different snapshots. When you want to recreate the picture, you add it all up. So here, if we wanted to draw the cat, we'd break up the cat into a bunch of tiny little snapshots, add them up, and then we'd have the cat again. So we want to see what happens if we add different parts of these snapshots. So if we have the first one, it's just a blurry mess. But if you add like 10 of them, you can start seeing the cat again. And if you have 50 of them, you get something that really resembles the cat. And it turns out that because each of these snapshots has about 0.1% of the information of the original image, you can recreate basically what you had with the original image at about 2% of the data. So if you use 2% of the data, you have something that resembles the cat, but it has a little bit less detail. If you go up to 5%, you get more of the detail. And if you keep adding more and more snapshots, you keep getting smaller and smaller details. So if we're interested in really the biggest parts, we want to really figure out what snapshots contribute the most to the picture. So once we identify which of these snapshots contribute the most to the picture, we know which ones to use when we recreate the image. What if we use some of these ideas in understanding turbulence? So what if we're able to get a turbulent field and create some snapshots so that we don't have to understand all the details of the turbulence, but just understand the really important parts? Well, for that, you need to find out a way to recreate these snapshots. One way that people recreate the snapshots is just by using the data and using basically the same idea as with the picture of the cat, and then just representing it in different snapshots. So you can see that each of these snapshots is trying to recreate this airfoil, and each of the snapshots just has a different part of the fluid or a different part of the behavior. And if you add it up, you recreate the image on the right. Another way is by using the equations. So the equations actually let us separate the fluid into different sized vortices and rate them based on their energy. So if you're able to do this for a turbulent field, you're able to get a series of different snapshots that you can use to recreate some of the stuff we see in turbulence. So if you use a few snapshots, you're able to recreate some things that you find in experiments. So here we used a few snapshots, and we're able to recreate the picture in the green, which is basically a visualization from an experiment. And you can see that although it doesn't get all the details, it's able to get a lot of the main ideas and the main behavior that you see in the original experiment. And the reason we want to use some of these models is because you can not only target different things with different length scales. So if we know, for example, that we want to see things on the size of a length of hair like the shark skin, that we can try to target that. And it would also let us simulate quickly how changing different patterns affect the field. So for example, if we wanted to try out different patterns on the surface of an airplane wing, one thing we can try is maybe designing something that's similar to shark skin and putting it on an airplane. And there's several patterns we can use, but using a reduced order model would help us test a lot of these very quickly. So in conclusion, I just want to repeat the quote again. So life is like the Navier-Stokes equations. It may seem complicated at first, but once you identify the important terms, it will become clear how to make progress. So in the first case we looked at, we tried to linearize the flow. So we were able to make predictions based on the stability of the flow, based on simplifying the equations. And what people do now, which is more modern, is by looking at snapshots of the flow and trying to use those snapshots to recreate the full picture that we had. I'd like to thank you all for watching the presentation.
Thank you, Salvador, for your fascinating presentation. This website also has a link that you can use to ask Salvador questions. He will be responding online within 48 hours of the premiere showing of this lecture. I also want to thank Mitch Aiken and Kitty Cahalan of Caltech's Teaching, Learning, and Outreach Office, as well as Mary Herrera from the Office of Public Programming, and the entire academic media technology team and the team from Event Productions. And thank you to the Caltech Employees Federal Credit Union, the Friends of Beckman Auditorium, and our many sponsors who make these types of programs possible. We look forward to your joining us again for other performing arts events and science lectures, which you can find out about by checking our website, events.caltech.edu. Thank you for joining us.